بالله من الشيطان الرجيم بسم الله الرحمن الرحيم
Assalamu alaikum, dear fellows. I'm Asad Abbas. My presentation topic is scanning electron microscope and electron diffraction technique. It's our lecture number 3.8, MS Chemistry, course code Chem 5134. During my presentation, I'll throw light on the topics components of scanning electron microscope, how a scanning electron microscope works, sample electron interactions, how is the path of electrons controlled, what kind of electrons are there, electron diffraction techniques, electron diffraction patterns, advantages and disadvantages of scanning electron microscope, and then applications and its limitations. So let us first define the scanning electron microscope. A scanning electron microscope is a type of electron microscope that produces image of a sample by scanning the surface with a focused beam of electrons. The electrons interact with atoms in the sample, producing various signals that contain information about the surface topography and composition of the sample. Now let us take a look at the main components of scanning electron microscope. They include source of electrons, column down which electrons travel with electromagnetic lenses, electron detector, sample chamber, computer and display to view the images. Electrons are produced at the top of the column, accelerated down and passed through a combination of lenses and apertures to produce a focused beam of electrons, which hits the surface of the sample. The sample is mounted on a stage in the chamber area, and unless the microscope is designed to operate at low vacuums, both the columns and the chamber are evacuated by a combination of pumps. The level of the vacuum will depend on the design of the microscope. The position of the electron beam on the sample is controlled by scanning coils situated above the objective lens. These coils allow the beam to scan over the surface of the sample. This beam enables information about a defined area on the sample to be collected. As a result of the electron sample interaction, a number of signals are produced. These signals are then detected by appropriate detector. Here is the schematic diagram of scanning electron microscope. Here you see the electron gun is at the top of the chambers. The electron beam is shown with red colors and the lenses are shown with diagonal lines. You see that electron gun produces electrons from top of the chamber and electrons are descend down towards the chambers and passing between the lenses. The electron beam strikes to the sample. After striking to the sample, the electron beam is moved toward detector, and after the detection it gives us the image that is scanned surface of the specimen. So let us discuss that what are the interactions that take place between the sample and electrons that give us the scanned image. So the scanning electron microscope produces image by scanning the sample with a high energy beam of electrons. As the electrons interact with the sample, they produce secondary electrons, backscattered electrons, and characteristic X-rays. These signals are collected by one or more detectors to form images which are then displayed on the computer screen. When the electron beam hits the surface of the sample, it penetrates the sample to a depth of few microns, depending on the accelerating voltage and density of the sample. Many signals like secondary electrons and X-rays are produced as a result of this interaction inside the sample. Here is the schematic electron beam interaction diagram. In this diagram, you can see the secondary electrons that are shown with green color. These are after the scattering from the sample. After these secondary electrons, some area is shown with light yellow color. This area shows characteristic X-rays of that sample. And then some continuum X-ray and fluorescent X-rays are shown in the downward worlds. The maximum resolution obtained in a scanning electron microscope depends on multiple factors like the electron spot size and interaction volume of the electron beam with the sample. While it cannot provide atomic resolution, some scanning electron microscopes can achieve resolution below 1 nanometer. Typical modern full-sized scanning electron microscopes provide resolution between 1 to 20 nanometers, whereas desktop system can provide a resolution of 20 nanometer or more. Here the question arises that how is the path of electrons controlled, because electron beam can converge or diverge. So in a similar way to optical microscopes, lenses are used to control the path of electrons. Because electrons cannot pass through glass, the lenses that are used here are electromagnetic. They simply consist of coils of wires inside metal pole pieces. When current passes through the coils, a magnetic field is generated. As electrons are very sensitive to magnetic fields, their path inside the microscope column can be controlled by these electromagnetic lenses, simply by adjusting the current that is applied to them. Generally, two types of electromagnetic lenses are used. The first is the condenser lens is the first lens that electrons meet as they travel toward the sample. This lens converges the beam before the electron beam cone opens again and is converged once more by the objective lens before hitting the sample. The condenser lens defines the size of the electron beam, which defines the resolution, while the main role of the objective lens is to focus the beam onto the sample. The scanning electron microscope's lens system also contains scanning coils, which are used to raster the beam onto the sample. In many cases, apertures are combined with the lenses in order to control the size of the beam. The main component of typical scanning electron microscope are shown in this schematic diagram. Here, electron source is shown with the yellow color and the electron beams are shown with the greenish color. You see that electron beam coming from the electron source passes in between the anodes. Here anodes are used for widening the beam of electron, because anode contains positive charge and electron contain negative charge, so the electron beam becomes widened while passing through the anodes. After this, condenser lens again converges the beam of electrons. Then scan coils makes the electrons beam a spot. After passing through the scan coil, the electron beam strikes the object lens and then strikes at the sample. From the sample, the electrons scattered are detected by the secondary electron detector. Now, question is this: what kind of electrons are there? The interaction of electrons with a sample can result in the generation of many different types of electrons, photons, or irradiations. In the case of scanning electron microscope, the two of the electrons are used for the imaging are the backscattered electrons and the secondary electrons. Backscattered electrons belong to the primary electron beam and are reflected back after elastic interactions between the beam and the sample. On the other hand, secondary electrons originate from the atoms of the sample. They are a result of inelastic interaction between the electron beam and the sample. Backscattered electrons come from deeper region of the sample while scattered electrons originate from surface regions. Therefore, backscattered electrons and scattered electrons carry different types of informations. Backscattered electrons images show high sensitivity to differences in the atomic number. The higher the atomic number, the brighter the material appears in the image. In this schematic diagram, different types of signals that are used by scanning electron microscope and the area from which these signals are originating is shown. You see here the yellowish colored incoming electron beam. After striking the sample, that is shown by the dark color, these electrons become scattered and become secondary electrons from the surface, and that electron penetrate inside the sample. They become backscattered electron as shown at the dark violet part of the figure. Then the electrons that are more penetrated inside the sample, they come back in the form of X-rays that are shown with a red color in the diagram. The two types of electrons, backscattered electrons and secondary electrons, can provide images, but the secondary electron imaging can provide more detailed surface information. In many microscopes detection, the X-rays which are generated from the electron-matter interaction is also widely used to perform elemental analysis of the sample. Every material produces X-rays that have a specific energy. X-rays are material's fingerprint. So, by detecting the energies of X-rays that come out of a sample with an unknown composition, it is possible to identify all the different elements that it contains. Here are the two figures that are made by different types of electrons. First is made the picture A, that is made by the backscattered electrons, and the picture B is made by the secondary electrons. These both pictures are of iron oxide particles. Here are the schematic diagrams for telling us that how the secondary electron, backscattered electron and X-rays are produced. In the first upper diagram, you can see that primary electrons are shown with red color. These primary electrons strike with the electron of atom, and the electron of atom gets higher energy and excited and moves out of the atom. These electrons are secondary electrons. But if the primary electron cannot strike the surface electrons, then it penetrates beneath the nucleus and then it strikes to the lower electron. Then the primary electron itself is backscattered, so it produces the backscattered electrons. Afterwards, the third diagram shows that the primary electron, when removes the secondary electron, then the electron of the outer shell comes in at the place of secondary electron, and the energy emitted by this electron is shown in the form of characteristic X-ray. Let us discuss the different electron diffraction techniques. The electron diffraction techniques can be divided on the basis of energy, geometry, and the beam type of electrons. Here we know that energy may be high or low. Geometry may be differ from transmission or reflection, and the beam of electron may be parallel or convergent. So by this type of different parameters, we can classify electron diffraction techniques into different types. Here are high energy electron diffraction, low energy electron diffraction, transmission high energy electron diffraction, reflection high energy electron diffraction, selected area, nano area, and convergent beam electron diffraction, large angle convergent beam electron diffraction. In this diagram, the electron diffraction technique is classified on the different bases. We say energy, geometry, and beam. Let us discuss how low energy electron diffraction microscope works. A beam of electrons of well-defined low energy is incident normally on the sample. The energy of the beam may range from 20 to 200 electron volts. The diffraction electron can be observed by a fluorescent screen after energy filtering grids, which selects only the electrons with the same kinetic energy as primary electron, and all this mechanism is shown in the diagram below, where the electron gun is producing electrons of varying energy from 20 to 200 electron volts. Here, after the production of electron beam is directed toward the crystals, and after striking the crystal, the electron beam is scattered and moves back towards the grids of the screen. Now let us discuss reflection, a high energy electron diffraction technique. In this technique, electrons of very high energy, near about 5 to 100 kilo electron volt energy, are directed toward the sample at nearly the 90-degree angle. This angle keeps very long path length of the electrons in near surface origin to increase the surface sensitivity and also to have K component comparable with the G of the crystal. Forward diffracted electrons strike phosphor screen. This phosphor screen shows that where are the electrons striking. Grid used to repel secondary and inelastically scattered electrons. Here the 5 kilo electron volt energy electrons have its parameter 0.055 angstrom and K component is equal to 114 per angstrom. Here are the schematic diagrams for telling us that how the secondary electron, backscattered electron and X-rays are produced. In the first upper diagram, you can see that primary electrons are shown with red color. These primary electrons strike with the electron of atom, and the electron of atom gets higher energy and excited and moves out of the atom. These electrons are secondary electrons. But if the primary electron cannot strike the surface electrons, then it penetrates beneath the nucleus and then it strikes to the lower electron. Then the primary electron itself is backscattered, so it produces the backscattered electrons. Afterwards, the third diagram shows that the primary electron, when removes the secondary electron, then the electron of the outer shell comes in at the place of secondary electron, and the energy emitted by this electron is shown in the form of characteristic X-ray. Here we will discuss how the patterns of single crystals are produced. Each diffraction spot corresponds to a single crystal. The distribution of diffraction spots is dependent on the crystal structure and the orientation of the crystal in the diffractometer. The diffracting condition is best illustrated with the evolved sphere's reciprocal space that is shown in the diagram. Diffraction spots are sometimes called reflection. After the discussion of single crystal material, let us discuss the pattern formation for the polycrystalline material. Polycrystalline materials are made up of many tiny single crystals. Most common metal material like copper pipes, nickel coins, stainless steel forks, or polycrystalline crystals. The single crystal grains in a polycrystal will have a random distribution of all the possible orientations. Ground up powder sample appears polycrystalline. A polycrystal is not as ordered as single crystal. An electron beam passing through a polycrystal will produce a diffraction pattern equivalent to that produced by a beam passing through series of single crystals of various orientations. The diffraction pattern will therefore look like a superposition of single crystal spot patterns. A series of concentric rings result from many spots very close together at various rotations around the center beam spot. From the diffraction rings, one can also determine the type of the polycrystalline material. Polycrystalline materials are made up of tiny single crystal, not ordered single crystal grains in a polycrystal have random distribution of all possible orientations. Diffraction pattern will look like superposition of single crystal spot pattern. A series of concentric rings result from many spots very close together at various rotation around the crystal spots. From the diffraction rings, type of crystal structure and lattice parameter can be determined. By one can not determine the orientation of polycrystal since there is no single orientation, and flipping or turning of the polycrystal will yield the same ring pattern. Pattern from the amorphous material. The amorphous material do not consist of atoms arranged in ordered lattice but in the hoggy-poggy random sites. Amorphous materials are completely disordered. The electron diffraction will consist of fuzzy rings of light on the fluorescent screen. The diameter of these rings of light are related to the average nearest neighbor distance of the material. Let us sum up whole the discussion about the patterns. Diffraction pattern give crystallographic information about a material from site-specific small values, unlike XRD, which is bulk analysis technique. We can determine if a material is amorphous, crystalline, or polycrystalline quickly and effectively by using these electron diffraction patterns. Lattice parameters information, unit cell details, any periodicity present in the sample arising from structural transformations or ordering processes can be seen. Superlattice structure gives information about the long-range makeup of materials. Here there are three diagrams of different types of material. The first diagram is from amorphous material, and you see that there is some hazy picture that there is no clear circle of the crystals, but in the second picture you see the clear spots of atoms that are present in the single crystal. And third is the picture of polycrystalline material that gives us concentric circles, from where it is clear that the material used is polycrystalline. Let us discuss the types of electron diffraction pattern on the basis of the geometry of pattern. There are two types of pattern, a ring pattern and spot pattern. A ring pattern arises from polycrystalline specimen. Major use of this is identification of the phases, analysis of texture, determination of the camera constant. But in spot pattern that is originated from single crystalline material, major uses of this pattern is the foil orientation can be determined, identification of phases can be done, and the orientation relationship between structure and structure can be determined. Let us discuss the advantages and disadvantages of electron diffraction techniques. Diffracted beam has high intensity can handle nano-size crystal, material needed in small amounts, cell symmetry, and cell parameter can be easily extracted from electron diffraction patterns. In transmission electron microscope and scanning electron microscope, particles are individually examined and particle shape can be measured. But take a look at the disadvantages of electron diffraction technique. More expensive, more time consuming must be done in high vacuum, and only transmission electron microscopes are capable doing this sort of microscopy. The transmission electron microscopes are extremely expensive. Samples that are prepared for the electron diffraction must be extremely thin. Samples of materials such as emulsions are difficult to prepare. These microscopes has low throughput, not used be routinely. Let us discuss how low energy electron diffraction microscope works. A beam of electrons of well-defined low energy is incident normally on the sample. The energy of the beam may range from 20 to 200 electron volts. The diffraction electron can be observed by a fluorescent screen after energy filtering grids, which selects only the electrons with the same kinetic energy as primary electron, and all this mechanism is shown in the diagram below, where the electron gun is producing electrons of varying energy from 20 to 200 electron volts. Here, after the production of electron beam is directed toward the crystals, and after striking the crystal, the electron. The more details of all these techniques are here. X-ray is cheapest and the most convenient and widely used method. X-ray interact with the spatial distribution of valence electrons, but the electron diffraction beam can easily produced by cathode tube easily available. This is in the case of electron diffraction technique. Electrons are charged particles and interact with matter through the Coulombic forces. This means that the incident electron feel the influence of both the positively charged atomic nuclei. In the case of neutron diffraction technique, neutron source is the world are limited to the neutron diffraction is a very special tool and very expensive. Neutrons are scattered by the atomic nuclei through the strong nuclear forces. In addition, the magnetic moment of neutron is non-zero and they are therefore also scattered by magnetic fields. Now it's time to discuss the application of electron diffraction techniques. The application of electron diffraction techniques include crystal orientation, phase identification, microstructure determination, texture determination, strain determination, and structure determination. In biology field, electron diffraction technique provides valuable information for evaluating specimen damage that can occur either during specimen preparation or while electron beam. Dark field electron microscopy can be used both to enhance the image contrast and to provide high enhance image contrast and provide highly restricted and highly specific information about the object. In the field of pharmaceutical industry, electron diffraction has been recently used in the pharmaceutical industry to study the polymorphism in the crystalline drug substances. In mineralogy, electron diffraction combines with electron microscopy is used to study mineralogical problems. In structure characterization, the electron diffraction combined with bright and dark field observation of the sample provide an efficient way to determine crystal structure related to specific morphology. Low energy electron diffraction technique is one of the most informative technique for determining the arrangement of atoms close to the surface. In the lead, which is used in chemical analysis, low electron diffraction technique, low energy electron diffraction technique patterns are used to access the defect density. Let us have an account of limitations of electron diffraction technique. The electron diffraction has following limitations, like a sample to be studied must be electron transparent, meaning the sample thickness must be of the order of 100 nanometer or less. Now, this technique is not applicable to the sample which are vulnerable to radiation damage caused by the incident electrons. This is also not applicable for the study of magnetic materials because of fact that electrons are deflected in the magnetic fields by the Lorentz force. Dear fellows, this is the end of my presentation. Your queries are warmly welcomed and I'm here to answer you all. Thank you very much. Take care.